So the Arrhenius equation relates the constant, the rate constant, with the collision factor, the steric factor, and also activation energy. And so the Arrhenius equation is given as rate constant is equal to collision factor times steric factor times Euler's number raised to the power negative activation energy divided by RT. E is called Euler's number, that is a constant 2.7. ZP, this is the collision factor, telling us how many, collision frequency, how many collisions are happening in a chemical reaction per second. P is the steric factor, telling us how many collisions are happening in a chemical reaction with the proper molecular orientation. So the combination of ZP and the combination of Z and P gives us what is called the frequency factor, which is given by A. And then that will be E to the power negative EA divided by RT. Now A, the frequency factor, is the collision frequency times the steric factor, and we've defined the frequency factor A as the number of collisions happening in a chemical reaction per second with a proper molecular orientation. So that is how we define it. Now, to make this equation in a linear form, we are going to introduce natural log on both sides. So introduce natural log here, introduce natural log there, and that gives us natural log of k is equal to natural log of A plus natural log of e to the power negative EA divided by RT. And how has this come about? When we have got a natural log of A, B, this is as good as saying natural log of A plus natural log of B. So whenever these two are multiplying, we can actually separate them with a plus here. That is why we've separated this and this with a plus, because we have introduced natural log. That is a rule of logarithms. So at this point, what we're going to have is natural log of k being equal to natural log of A. At the same time, when you've got natural log of something, or let's just say, okay, natural log of A to the power x can also be written as x natural log of A. So natural log of e to the power this, we can actually drop that, it comes down, and that is going to be negative activation energy divided by RT, and then natural log of e. Well, natural log of e is equal to 1 because they are inverses of each other. So where there is natural log of e, we're going to put a 1. So this becomes a natural log of k is equal to natural log of A minus EA divided by RT. I can as well rearrange this starting with this portion here, and then so I'll just swap these two. So that becomes a natural log of k being equal to negative. I can as well say activation energy over R, and then write the temperature alone 1 over T, and then plus natural log of A. So all I've done is I've split this like that. It's the same thing if we did multiply this and this. So this is the linear form of the Arrhenius equation, which we need to know. So this is in the form y is equal to mx plus c, where the gradient m is given by negative activation energy divided by r, and then the y-intercept is the natural log of A. The y-axis is represented by natural log of k, and then the x-axis is represented by 1 over temperature in Kelvin. And so just at this point, let's say we are talking of two temperatures, at temperature 1 and temperature 2. So what we are going to have is natural log of, so we are also going to have K1 and K2, since we have got two different temperatures. And so just this equation we can see we're going to say natural log of K1 is going to be equal to negative activation energy divided by R, and then we are going to have 1 over T1 and then plus natural log of A. Writing it again now with temperature 2 becomes natural log of K2 being equal to negative activation energy divided by R, and then 1 over temperature 2 and then plus natural log of A. So this is the form that we are going to get, where I can as well just go on and say natural log of K1 is equal to negative EA divided by RT1 I've multiplied plus natural log of A, and then I've got natural log of K2 being equal to negative EA divided by RT2 plus natural log of A. Now at this point what we're going to do, let's say this is equation 1, the first one as equation 1, this as equation 2. So we're going to subtract equation 1 from equation 2. So doing that, what we are going to get is, we are saying subtract 1 from 2. So subtracting 1 from 2, we are going to have natural log of K2 minus natural log of K1. So I've started with this portion, we've subtracted it. And then we're going to go on and subtract also the other side. We have got negative activation energy over RT2 plus natural log of A, and then we are subtracting. Okay, we subtract now this portion we've written it there. So now we subtract this portion from equation 1, that is negative EL divided by RT1 and then plus natural log of A, where this negative is going to be distributed, and so we know that natural log of A minus natural log of B is the same as natural log of A over B. So we can actually write this as K2 over K1. So that becomes natural log of K2 divided by K1 is equal to negative activation energy over RT2 plus natural log of A. This times this becomes positive, so that would be positive activation energy over RT1, and then this by that is going to become negative. Okay, that will be now negative natural log of A. Well, at this point we can notice some things. We have got natural log of A positive and this one, which will be able to cancel out. Okay, so those are going to be able to cancel out like that. And so from this point, let's go on and rewrite it all the more. So that is going to leave natural log of K2 divided by K1 being equal to, let's start with this portion which is positive. So that would be EA over RT1. These won't be able to subtract because we have got T1, T2 here, and then this is T1. So we can't subtract them even if they've got opposite signs. And then minus, we'll now write this one, which is activation energy divided by RT2. Now we can see activation energy is the same, R is the same on both sides, so we can factorize out that. So we're going to have natural log of K2 divided by K1 being equal to activation energy divided by R, and then what we have is 1 over T1 minus 1 over T2. So this is the form of the Arrhenius equation which we work with when you've been given two different temperatures and two different rate constants to be able to determine the activation energy. Now let's look at an example. We see how to apply this. The following data was collected at different temperatures. So you've got a rate constant K, which is in liter per mole second, and then you've got the temperature, which is in Kelvin. The first rate constant, let's say this is K1, and then this is K2, and then let's say this is T1, and then this is T2. Now the question is, calculate the activation energy. Well, using the formula, natural log of K2 divided by K1 is equal to activation energy over R, then we've got 1 over T1 minus 1 over T2. So this will give us natural log K2, we can see is there, that is 6.4, divided by K1, which is 1.1, and that is going to be equal to activation energy we don't know. Now the rate constant we know is R, which is the universal gas constant, 8.3145. It is in joules per mole Kelvin. And then we've got 1 over temperature 1, it's 823, minus 1 over temperature 2 is 898. So this will give us, now if we say 6.4 divided by 1.1, and then the answer we get, we say natural log of the answer that we get, supposed to get 1.7609878811, and that is going to be equal to activation energy over 8.3145. Then we have got 1 over 823 minus 1 over 898, that is going to give 75 divided by 739054. And so at this point what we can do is we can go on and multiply this one in the denominator, multiply by this one in the denominator. The answer that we are going to get, we are going to divide it into 75. So what we'll get is 1.7609878811 being equal to activation energy times 0.000012205. Well, to remain with the activation energy, we are just going to divide by this number we can see on both sides. So the activation energy is going to give us 144,284.1303, which we can as well just write in standard form as 1.4. The decimal point is here to move 1, 2, 3, 4, 5. So it has moved 5 times. So that is 1.4 times 10 to the power 5. So the unit is joule per mole. So that is how we get to apply this form of the Arrhenius equation to answer questions.